about all of this is that that mercury spectrum is indicative of mercury, and notice it is an emission spectrum, and so we don't have to be really anywhere near the source to detect the atoms that are in that source. Really? I mean, you're pretty far away from that light, and yet you're able to look at it through this diffraction lens and see the emission of that light. So without even getting anywhere near that tube light, you can tell there's mercury in that tube light. If we shine a telescope at a distant star and we see those same photons, we know there's mercury in that distant star. And so you can do spectroscopy on distant objects. When I first discovered this, it just blew my mind. I thought, this is amazing. Now, this is a natural place to put this in the notes because we are looking at atomic spectra. And that's this sort of the simplest, cleanest spectrum. We can look at distant stars and see the hot atoms that are emitting light. And we can see the composition of those stars by looking for the different elements. So it's pretty amazing. So I just always stick this right in here. We've really pretty much covered everything that's going to be on the test on Monday. So this is what you would call enrichment. Okay, a little extra stuff at this part of the notes. Now I would like for you to be comfortable using Hubble's law and converting, expansion distance or redshift values into distance. So it's just a couple of equations in these notes, and there's a couple of examples of those calculations in these notes. So just if you can do the two calculations we have in these notes, then you're good. But I really want you to just kind of sit back and think about what we're doing. We're doing spectroscopy on objects that we have no hope of ever reaching. Okay. So here's a spectrum, a visible spectrum that I took through my office window. So I had the little USB spectrometer that you guys used for the color lab, and I just aimed it out the window and caught the spectrum of the sun. Now I'm looking at the continuous emission, so we have pretty much all wavelengths of light. It's a rainbow, right? Uh-oh, whoever's charging their phone. Might check on that. Okay, so you get this black body profile. You see that the emission goes up from the red as you get to the blue, then it drops off in the deep blue, the UV catastrophe, remember all of those kinds of things with the black body radiation. So that's the generic or continuous source profile of our sun. And then you notice there's certain little dips. So look at some of these dips. These dark lines, like here's a big dip in the purple region, and you get into the red, you see a dip there. So these lines here, these dark lines, and you can see them with the older Cheez-It spectrometer. If you go outside on a sunny day and look at the sun, you'll see some dark spots. You'll get a full rainbow, but then horizontally there'll be some dark lines. There'll be light missing. And that's really interesting. Where'd that light go? When the sun's emitting all wavelengths of light, and yet when you detect it, you're missing some. Well, let's look here. Here's a couple of dips at A and B, and those lines are oxygen. Well, gosh, that makes sense, doesn't it? So we're looking through our atmosphere, and our atmosphere has oxygen in it. And so as that sunlight's coming through, the oxygen is absorbing some of that sunlight. So this is kind of cool. We could do spectroscopy on our own atmosphere, just using the source as the sun as our source. And you can do this too at sunset. You can send up a weather balloon and have it look at the sun and collect spectra versus altitude. As you get higher and higher, you could look at the changes in the spectrum. So that's pretty cool. So let's go on down. What is this C line? Okay, C, pretty dark line, and it says hydrogen. Uh-oh. And D, that's sodium. Now, I don't know about you, but we don't have a lot of hydrogen in our atmosphere, okay? We have an oxidizing atmosphere. So if there was hydrogen that got away from one of our experiments, as soon as it got into the room, oxygen would chew it up and make water, okay? And sodium, we really don't have a lot of sodium in the atmosphere. So these Fraunhofer lines were a strange discovery. Oxygen made sense, but sodium does not make sense. And even here, if we go further down to E, this is iron. We don't have a lot of iron in our atmosphere. So where are this atomic sodium and atomic iron coming from? So here's our sun, And as you might imagine, it's blowing away a lot of gas. It's a fusion reactor, and it's blowing off a lot of elements. And so there's a cloud around our sun of heavy elements that have been blown out, and they cool, and then they get sucked back in by gravity. Some of them escape, and that's our solar wind that we have. These are elements that have been blown away from the sun so strongly that they escape, but those are typically hydrogen atoms or protons. The iron and sodium are going to be recollected by the sun, but we have this gaseous cloud around our sun. So all of those wavelengths that are leaving our sun are filtered by these cold atoms that are on the outside of the sun, and so we're missing that yellow line. You see, it's missing. So sodium atom that's in the cloud around our sun has absorbed that yellow line. So we're able to see the atmosphere around our sun. And our sun's not unique. We could look at any star and detect the missing wavelengths of light and know something about the composition of that star. So this is how we do not just stellar spectroscopy, but how we understand how old a star is. Because you can look at the fusion reactor in that sun or that star, and it's generating heavy elements over its lifetime. And you can kind of see how mature a star is by looking for the amount of iron versus magnesium, or iron versus sodium, and they've got a nice lifetime plot of these different stars, and you can look at them. Then that lifetime plot is also related to how bright it is. And so you can use the different wavelengths of light. Here's this galaxy that's imaged with different spectral detectors, UV all the way down into the infrared, and so they make this nice composite image in the middle. And so this is again, just looking at the emission of different elements in all of those different stars tells us something about them. So this kind of fits with our standard cosmological model. So this, let me just talk about our latest understanding of the universe. We don't really know what happened at the beginning. They say quantum fluctuations, but that's a claim that's, not very strongly supported. We don't know what started it. But we do, most of the models call for some sort of rapid expansion. Now that rapid expansion requires physics that we don't know about, okay? That's faster than the speed of light. So everything is spread out nearly immediately. 10 to the minus 30 seconds is pretty close to nearly immediately. Okay, and so, Megan, let me have you come up. Kyler, you come up. So we're going to be 3 stars that are spread out immediately, okay? So ready, we go spread out, 10 to the minus 34 seconds. So get it far away from me, okay? All right, that's good right there. And then we coalesce. We weren't stars at the beginning, but there's fluctuations in the amount of gravity and so on. And so then we start to collect material, hydrogen, and we start to emit light. So this dark, see this dark ages? That's not the medieval times, that's really the old dark ages. Okay. Then we start emitting light. So we're already like 14 billion light years apart. So then we start emitting light. So you emit some light, very good, he's emitting light, you're emitting light. And now it takes a long time for that light to meet us, the observers. Okay. So we were spread out that far very quickly, and then we started emitting light. And so the farther away we look in the galaxy, we're also looking back into the past. So like I might see your light here, and if I look at the redshift, I calculate your distance, and it took 65 million light years for your light to get to me. But I look in the darkest region of the universe, and I'm over here, and I'm like, oh my gosh, that's the faintest star I've ever seen. And it's got a sodium doublet, it looks like, but it's way redshifted. It's the oldest light I've ever seen. And it calculates to be 13.7 billion years old. So y'all can sit down. Let's give them a hand. So we have 2 things happening. We don't have much information about the initial inflation because things weren't even emitting light at that time. But we do have a lot about, see how this cone kind of stretches out a little bit? We do have a lot of information about this expanding part of the universe. So Einstein was troubled by his theory of general relativity that it required an expanding universe. And he didn't really know what to do with that. And then Edwin Hubble noticed that sodium lines and other well-known lines, because of the same kinds of splitting that we're doing with the term symbols, he knew that sodium, this doublet is a sodium doublet, and on, say, an Andromeda galaxy, it's shifted red. And in a further galaxy, it's shifted even more red. And one way to understand that shift is for an expanding universe. So Einstein predicted it with his theory, and Hubble sort of said, yeah, that matches what we see. And so that's why they call it the Hubble constant. Okay. So this is evidence for this expanding universe, is this cosmological redshift. So I always wondered, was it just the whole emission spectrum of the star that's shifted red? How would we know? You know, you say, how can you tell if this continuum is more red than it should be? Because how do you know what it should be, right? That's what my question was. How do you know it's really red shifted? We know because of atomic spectra. So the sodium doublet, this doublet P 1/2 and doublet P 3/2 emitting down to the singlet S0, that's, or the doublet S0, doublet S 1/2, that emission doublet is a signature for sodium. So when we see that in the far red part of the spectrum, we know that emission line has been redshifted. Now, what does it mean by redshifted? So if I'm looking at you and I'm giving you 589 nanometer light, but I start moving away, to you it looks slower. Okay, so this is the Doppler effect. As we're moving away, that wavelength is hitting you, but it's hitting you with a longer wavelength. And so even though we're moving away from each other, sodium's still emitting 589 light, but you see it as 590 nanometer light because of the expansion. So that all that is shown here as those dark lines, those Fraunhofer lines, for a distant star will be shifted towards the red. We know they're the sodium, the iron, the magnesium, the calcium lines because of the spin-spin splitting of the electron in their orbitals. So we have the right little triplets and doublets and so on, but they're shifted to the red. And so we can calculate what they are on Earth, and then what they are observed through a telescope. And so we can just take this shift, the relative shift. So we take the difference and divide by what it is on Earth. And that would be that Z factor, that redshift factor. So in this particular example, it's only shifted by 0.4% or 0.47, so about 0.5% is what it's shifted. And so this, we can use the speed of light to figure out what velocity it's moving away from us to give us that kind of shift. This is a very sensitive technique. And so if you multiply that by the speed of light in kilometers per second because of the magnitudes of the speeds that we're dealing with, and that's receding from us at 1,425 kilometers per second. That's pretty fast. 1,000 kilometers per second. I don't drive that fast. I drive fast, but not that fast. Okay, so that's the rate at which that star is moving away from us, and that's the expansion rate of when that light left that star. So we're kind of getting the expansion rate over time. So if I looked at the most distant galaxy, it would be even further, a faster expansion rate. Now this is Hubble's law. We had to do two things to get Hubble's law. One, we needed to know something about this expansion rate and correlate that to distance. So if we were able to measure the redshift of a distant galaxy, how far away is it? This is the equation that we're trying to sort of map out our universe. Now, for near distances, we can use orbital parallax. So think about 3D glasses or 3D cameras. They need two lenses, don't they? Because you have two eyes. And I can tell that that Ever is further back than Kyle because my eyes can see two different pictures. And my brain says, wow, I've got two different pictures here. One way to reconcile this signal is to give them depth. And so these two images superimposed can be used to get depth. The parallax is seeing those two images from different angles. So what are the biggest angles we can get on Earth? Well, yeah, we could put a spectrometer in California and one in Massachusetts, okay? But that's not a very big distance. Let's do one in the fall and one in the spring. Yeah? You see what's going on? In the fall, you take a picture of the sky, and in the spring, you take a picture of the sky, and now our whole orbit is the parallax. So our eyeballs are the diameter of our orbit around the sun. And so we could take pictures of different regions in the sky every year, every day of every year, and depending on where we look, we can kind of map out the near galaxies and near stars. And then we can take their brightnesses in our little model for how the sun goes through its progression of heavy elements and how much light it emits, and we can correlate brightness with distance. That's key, because once we correlated brightness with distance, the distant objects, which really don't show up much in this parallax experiment, we can now use that brightness distance model for the further objects away, the objects that are further away. So all that is to say, we were able to calibrate this plot. So we can have the redshift on the y-axis and distance on the x-axis. And it's pretty amazing. These galaxies and stars fall right on that line. So the Hubble constant is a pretty linear relationship in distance and this redshift parameter. Now, what's going on with this business here in the middle? We've got at around the same distance, we've got a lot of stars that are moving faster away from us than these. And that right there, that whole cluster is rotating around itself. Like there's a supermassive black hole in the middle. And so even though those are all receding away from us, some are receding faster and some are receding slower, which means they're orbiting each other. And so that's a supermassive cluster that's orbiting it around a supermassive black hole. We're able to see that orbital rotation speed with this little vertical burst of stars. So we get it, we're in absolutely enormous distances. It's the distance light travels in a year, but even that wasn't enough, so now we're dealing with megaparsecs. This is the distance in megaparsecs. So 10 to the 6 is the megapart. A parsec is 3.26 light years. Okay. So I don't know how Han Solo did that, but anyways. So then we had the Hubble Constant, which is 70.4 plus or minus 1.4 at the time I looked it up. I'm sure these things are always being tweaked and made better. And so this is a pretty neat conversion. If we have the redshift that can tell us kilometers per second, then we can use the Hubble constant to tell how far this star was from us. So this is a way to get distance. You measure the redshift of the wavelengths of light for a known element. You have the speed of light, and now you know the Hubble constant, and that will give us the distance of that galaxy away from us. So let's practice. Let's take this one at 20 megaparsecs. What would the observed wavelength be? So this is the kind of calculation that I think you should be able to do. If you have this equation, be sure to put it on your note card. What would be the observed wavelength of a sodium 589.6 nanometer line from a star 20 megaparsecs away? And so here we have we're given the distance here, and we need to know, so we have this number, we have the speed of light, we have the Hubble constant, we have the Earth wavelength of sodium, and this is what we want. And so you got to do a little algebra, bring h over, bring c over, multiply both sides by e, lambda e, and so this, rearranging this equation gives us our observed wavelength. Putting all those numbers in, we end up with 592.4 nanometers. So that would be where that sodium line would show up in our telescope spectrometer. So we went to see the McDonald Observatory, and they're looking at all of the optics, the visible optics, and I'm over here underneath the belly of the telescope where the spectrometer is, and that's where the the monochromator is and the detector and everything, and I was just all excited about that. And the guy's looking at me like, what are you doing over there? So I said, I'm looking at your spectrometer. And he said, oh yeah. So then he started talking about stellar spectroscopy instead of just imaging things. Okay, so when did that emitted light leave that star? 20 megaparsecs away. Okay. And so if we look at 20 megaparsecs, a megaparsec is 3.26 times 10 to the 6 light years. And so it left 65 million years ago. And the reason we're detecting it now, 65 million years later, is because it took 65 million years for that light to leave that star. Okay. Now, how would we know how old that star actually is? We would look at its spectral profile and see how much iron it had and so on. And so we could look at the chemical nature of the whole star's spectrum. We could put it in this model to see how old that star is. But the light we get today is really a function of the distance of that star, because the speed of light is constant. So that light's hitting us. What about the light that hit us a million years ago? We just didn't detect it. It went on past us. Now, the really distant stars, their light has been traveling this whole time, and we're just now seeing it today. So we're looking back in time whenever we do spectroscopy in astronomy. You know, we're seeing the light that's leaving our sun 8 minutes after it left. So it takes 8 minutes for our sun's light to get to us. So my question was always, if the sun just sort of disappeared, would we know immediately, or would we know 8 minutes later? I don't know how the sun could disappear, but, you know, and that's the question of gravity. Does gravity travel at the speed of light or not? We did not know the answer to that question until in the past couple of years, that LIGO experiment, where they detected the collision of two black holes, and it sent a gravity wave. They had never before detected a gravity wave. And this gravity wave went through our planet, and the speed at which it traveled was the speed of light. So now we know the answer. If our sun disappeared, we'd detect the gravitational distance the same time the light went out. Okay. Because, you know, maybe you detect it immediately. Who knows? Is gravity limited by the speed of light? Well, now we know that it is. Okay, so crazy, crazy questions and crazy answers. So how many meters is this far away, 65 million years ago? You know, you can just take that years and convert it to days and hours and seconds, and then using the speed of light, meters per second, we get 6.1 times 10 to the 23rd meters away. So that's a long way. That's a mole of meters, just coincidentally. I don't know why. It doesn't really have any significance. But so long way. Last slide, I think. This is an excellent video with all these calculations on it, so you can follow that link in this lecture. This is physicist Michael on his YouTube channel. It's a good channel. Now, this is a long way away. So how do we know that the laws of physics, so what confidence do we have that physics was the same 65 million years ago as it is today? Well, this spin-orbit coupling is how we know. So think about what's going on with the sodium doublet. That is the splitting of the p orbital with the spin of the electron in that orbital, okay? And that spin-spin-splitting depends upon what they call the Bohr magneton, the electron G value, and the magnetic field. Now, if this website down here shows you how to use those equations and how to calculate that magnetic field. What's amazing is you put in the Bohr magneton and the G factor for the electron, and you calculate the magnetic field of that orbit, that p orbital that the electron is in, and it's like 18 Tesla. Okay, our NMR magnet that will erase your bank cards at 10 feet is not even 1 Tesla. This is way more than 18 times stronger than the magnet that we have upstairs in our NMR. That is an incredible magnetic field in this little p orbital. Okay. Anyway, that's just neither here nor there. But the thing about the physics is, look what's in that Bohr magneton. So that Bohr magneton has the charge on an electron right here. These are fundamental constants. Charge on an electron, Planck's constant, that bar means over 2 pi, and the mass of the electron. if any one of those constants had changed in the past 65 million years, then that doublet for sodium would look different. Do you follow me? That doublet in that sodium looks the same in that star that we're calculating as 65 million years ago, and in the star that's, 10 billion years ago, and so on. So it looks like physics isn't changing during this time. This is a debate that's not necessarily happening in science, but it's happening elsewhere. So the splitting and relative intensities have not changed in the spectra of any of these ancient stars. We see the red shift, but the doublets and triplets of these atomic emission lines appear to be the same. And that means that the charge on the fundamental particles of electrons and protons hasn't changed. Planck's constant hasn't changed. The mass of the electron hasn't changed. Okay, so this is an important piece of the debate. Okay, so let's do a Kahoot just to catch up on things. So let's do this to review our electron configurations and our trends in terms of the first ionization energies. Oh, that's loud. 907242. Be sure to use your 3 letters and 3 numbers, your email login ID. So. It did what? The pumpkins? Yeah, that's right. Spooktober. Yes, I'm on Reddit. Talking trash on Reddit all the time. Kim for all, you can find me. Troll me, I'll troll back. All right. Let's see, I didn't count up. Anybody? Are we waiting on anyone? Okay, let's go. So we're going to beat this to death. So do you think it's on the test? Yep. Give me a basic reason for the low first ionization energy for rubidium. This guy right here. So it has a low first ionization energy. Why? So your questions are, the answers are fully filled valence shells are stable, half-filled valence subshells are stable. Okay. So the top 2 are subshells are stable. And this is half-filled valence shells are stable, fully filled valence shells are stable. So you're having to parse the differences between those words. Okay, so we have a tie kind of between fully filled valence shells are stable and half-filled valence subshells are stable. And this is rubidium. Now, does it have a fully filled valence shell? No. But the cation does. Okay? So remember this. And it's got a low first ionization potential. So the cation is stable. So because the cation is stable, it has a low IE. Remember? Okay, so let's do the next one. Oops, gotta do it twice. Give a basic reason for the low first ionization energy for gallium. Ooh, dark. Gallium. Same choices. Fully filled valence subshells are stable. Half-filled valence subshells are stable. Half-filled valence shells are stable. Fully filled valence shells are stable. That's the spooktacular theme. Making me crawl under the desk. Oh no! It's a spread of almost the same. Good job on the 10, but so here we are at gallium. So this one was fully filled. So this was rubidium. And then for gallium, it also had a low one, but why was gallium low? Gallium plus has fully filled subshell. Right? Which subshell is that? Which subshell is fully filled in gallium cation? The 3D. Yeah, it's 3D10. Yep. Yes.
So what's the difference between the rubidium shell and the gallium subshell?
Rubidium, if you go to the cation for rubidium, it's krypton and noble gas. So the noble gases are the only ones that have fully filled valence shells. So I'm calculating the whole valence, all of the external electrons. And so your noble gases have fully filled valence shells, but group 2, fully filled S. Yep. Group whatever, fully filled D shell. And then once you get here, everything's full. We're not really dealing with the F block because it's totally nuts. So we'll just, if you get into the lanthanides and actinides, you know.
So what?
The cation, gallium cation. Okay, so here we are. We have the high first ionization energy for magnesium. Okay, high first ionization energy of magnesium. That's so creepy. Same 4 answers. Okay, still a pretty big spread. Now the correct answer is fully filled valence subshells are stable. So how does that figure in? We've got a high first ionization energy, so this orbital is actually a little more stable than what you would expect because it's a fully filled subshell. It's a 3s2. So it's 3s2, S2 is stable, that's 2 electrons in the s orbital, and so the neutral is a little bit lower than you'd expect, and that makes the ionization energy higher. Okay, let's try again. Give a basic reason for the high first ionization energy for nitrogen. I'm turning that down. Yeah, I know it. Just raise the stress level. Now, anytime you're dealing with an unusually high ionization energy, it's always the neutral that gets lower. And whenever you're dealing with a low ionization energy, it's always the cation that gets lower. So when we're talking about stability, you're either lowering the neutral or lowering the cation. Okay? But notice how you can't even think about this unless you understand electron configurations. So you got to be good with electron configurations to understand this. Now you know what I'm going to do. I'm going to give you an element, and I'm going to say do the electron configuration, and then use the energy level diagrams to explain it. So you're going to have to draw these energy level diagrams to explain things. So this is all on video. So you can go back and watch this Kahoot and learn how to draw what I've been drawing on the board. Use energy level diagrams whenever you can to explain what's going on in chemistry. Okay, that's why I often have a pen with me, because you never know, cocktail napkin to argue about things. And I always use energy level diagrams to do that. Okay, so that was the half-filled example for nitrogen. 5 of 5, last one. Give a basic reason for the low first ionization energy for oxygen.
Mine isn't loading.
Say again?
Mine isn't loading.
Oh no. You're gonna lose your streak.
Yeah.
I'm sorry. It's technology. That's why I don't actually look at the points you get. I just calculate whether you participated or not. So, okay. All right. So it's the same reason nitrogen is high as the reason that oxygen is low. So we have oxygen cation, oxygen neutral, but because the cation has a stable half-filled subshell, the ionization energy is lower. So 2p3. Okay. 2p4. So this has 2p4. It's one past a half-filled. The cation is half-filled, so it's a little bit more stable than you would expect, and so the ionization energy is lower than you'd expect. Yes?
So I have a question for the magnesium.
Yes.
Like the 3s subshell, if it was just half filled with sodium, isn't that technically stable too, or half filled?
Yes, and so you don't see much of a jump between these. You know, like nitrogen, they actually change place on the ionization chart, but you don't really see these swapping. You know, you get such a low ionization energy for the alkali metals because of the noble gas configuration of the cation, and then this probably should be a little higher than it is, but the cation is a half filled. Yeah. So you just don't really see an exception between those two. Yeah. That's good. Good observation. Okay, let's see who won. Dun, dun, dun. Yay. I don't know who these are, but good job. Yeah. So it's somewhat anonymous. So we can comply with FERPA. You know FERPA, don't you? Okay, so let's do another one. Okay. Fun with term symbols. All right. Let me just make sure that this is recording. I said it was. Yeah, it is. Okay. That would have been so sad. Okay, let's go. 800-714. Call them out. I went through and cleaned up the Quizlet. There's only 37 terms. It's not too bad. And then, yeah, so work on those. I locked it down so you can't add any more terms. That way you can study them and not have terms show up. It's like, wait a second, where does the word come from? Get together and do, Quizlet lives and things together, or do a Kahoots together. All right, let's go. 7 questions. What is the ground state term symbol for the noble gases? You're like, wait a minute, how can I do this so fast? But think about it. That's good though. Knocked it out. And again, since it's multiple choice, you ought to be able to eliminate some things. If anybody says red, I'm going to be crying. That was good. I'm going to cut that on the video. Play on loop. Yay, 14. Good job. Okay, so singlet S0. Everything's paired up, so the multiplicity is singlet because the zero net spin. Okay. That was golden. Play that for my mom. She's a teacher. Okay, why do beryllium and zinc, have the same ground state term symbol, singlet S0? That's some game. That's beryllium.
Yeah, it's gonna fall out.
So the options are, well, I don't have time to read the options. Okay, yay, look at that. Ooh. Okay, so where are they? Here's beryllium, fully filled subshell. Here's zinc, fully filled subshell. So all the spins are paired up. So you have a singlet, and then, S, because, again, they're full. If they're all full, it's an S term. 3 of 7. Quickly, what is the ground state term symbol for the alkali metals? So all of these first ones. The J value is the only one that's tricky on this, I think. Okay. Oh, it's so loud. Okay, so we're gonna reteach on this one. Yeah, so what have we got? I don't need to show the picture. We've got one unpaired electron, okay? And so then that's gonna be a doublet. Okay, so the multiplicity, that superscript on the left has to be a 2 for a single unpaired electron. So that allows you to eliminate half the options. Okay, so you look at it and go, it's gotta be a doublet, doublet something, okay? That electron's in an s orbital, so it's gonna be an s. And then what's that J value? That's L plus S. S is 1/2, L is 0. So L plus S would be 1/2. So a doublet S 1/2 is that ground state sodium. You heard me kind of, if you go back to the earlier, well, in the lecture I was talking about the sodium splitting, and I stumbled on the ground state, and I finally arrived at it. Doublet S, I said 0, but it's doublet S 1/2. So I was going through it in my mind, so you heard my thinking on that. How many unpaired electrons are in the atom with a triplet D3 term symbol? So a triplet D3 term symbol. If I give you that term symbol, you should be able to tell me how many unpaired electrons there are. Doesn't matter what the element is. Zero, 1, 2, or 3. I wish I could pause it. Okay. 2. Now, here's the thing. You've got 3 pieces of information in a term symbol. You've got the multiplicity, you got the term, and you got the J value. Which one of those is going to tell you how many unpaired electrons there are? The multiplicity. The multiplicity. And so it's a triplet. And that is equal to 2s plus 1. Okay? And so essentially you could just subtract 1 from that, and that tells you how many unpaired electrons you have. So if it's a triplet, you take away 1, you have 2 unpaired electrons. If it's a singlet, you take away 1, you have 0 unpaired electrons. What if it's a quartet? Take away 1, you have 3 unpaired electrons. I do a lot with counting on my fingers. It really helps. Like SPDF, okay? S is a sphere. P, D, F. Okay? The sphere is 0. What is L for a D orbital? S, P, D. Okay? What is it for an F orbital? S, P, D, F. 3. So that's how I do my L values. Okay? Very simple tools. I see on the exam. You know, that's fine. I'm not going to video you or anything. What is a D2 system? Well, with a D2 system, what is the full range of capital L? A D2 system. So we have 2 electrons in the D orbitals. It's the full range of L. This one takes a little time. That's why I gave you 60 seconds. Okay. See if I can do it up here real quick. L equals L1 plus L2, dot, 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 L1 minus L2. Full range. D orbital. S, P, D. 2 plus 2. 0. 4, 3, 2. Okay. So that's how you do it. Thinking, okay, where are my electrons? I have 2 electrons in the D orbital. What are these going to be? Max, min, subtract 1 in between. I didn't finish the work, did I? That's why y'all were looking at me so confusing. 1, 0. I was in a hurry. Yeah, that's embarrassing. Okay. So, with a D2 system, what's the full range of S? So in your little paper, right? So your S are your two spins on your electrons. You have two electrons. What are you going to do? Add them together, subtract them. Okay. I missed something funny.
He didn't wait.
Oh, I should have waited. Yeah. 60 seconds. Okay, the last two, go ahead and answer. I know you're just sitting there waiting. Yay, okay. You guys trying to make everybody late. All right, now we're getting strange. In a triplet F term, what are the J values? What? Triplet F term, what the heck? I won't do it for you this time, but remember it's L plus S. So that's what you're doing for the J values. What is S for a triplet? Silence. What is L for an F or term? S, P, D, F. You got 3. Multiplicity, triplet, that's 2S plus 1. So 3 minus 1, divide by 2. Okay, S is 1. So you have 3 plus 1, which is 4. 3 minus 1, which is 2. So then it goes 4, 3, 2. So it's this orange selection. Right? So if given the term, you should be able to pull out these pieces. So it's not just about going forward, it also may be such that you need to go backwards. So watch the Kahoot online. It's saved. It'll be posted later today. Great job.
What is your name on Kahoot?
CHEM_prof. So if you want to get to all my Kahoots, it's CHEM_prof. Yes?